Hey all you cool cats and kittens, it's Mr. DeRoss here. We're going to be continuing on in our notes regarding motion. And today we are going to be talking about what we call Newton's laws of motion. This is Sir Isaac Newton. I've also linked a video about him. He's probably one of the, if not the most famous scientist in history. And Newton was extremely intelligent scientist, and his work involved astronomy and mathematics and physics and optics, and one interesting fact about Newton is that during the time of the plague, when his university was shut down, so you can all relate to this, he didn't just go home and watch Netflix and obsess over the Tiger King. He developed calculus, the branch of mathematics called calculus. So I'm expecting some big things out of you guys when you're here on break. So maybe you could develop a new form of mathematics like Newton did. But Newton studied motion, and that's how we're going to be talking about him. So when Newton was thinking about how objects move, came up with a set of laws. We call this mechanics, classical mechanics. And he came up with a set of ideas about the rules that sort of govern how objects move. And today we call those Newton's laws of motion. And there's three laws that Newton developed that we still use today, and these laws apply. And we'll learn about each of them, learn about some examples. Tomorrow I'm going to ask you to watch some videos that will help you to understand sort of how these laws apply to everyday objects and how they're applicable to our lives. And then we're going to be doing some online simulations that concern these laws. So let's start with a definition here, force. So you're going to use this term a lot as we move into this section of the unit. A force is sometimes a little bit difficult to define. What we're going to say is that a force is a push or a pull or a lift on an object. It is an interaction that can cause an object to move. Okay. So we'll talk a lot about forces in this section. There's sort of two special categories of forces that we will also talk about. One is friction, one is gravity. So what exactly is friction? Probably it's a term you've heard before. Friction is a force that resists objects' motion. So for example, if you are walking on a hardwood floor with your socks on, okay, you could slide your feet over that floor and they'll move pretty smoothly. If you change and you put on your running shoes and try to do the same thing, obviously you're going to notice that you can't just slide your foot along the floor. That's because between the rubber and the soles of your running shoes and the floor, there's much greater amount of friction, which is resisting the movement of those objects across each other. Different types of surfaces have different amounts of friction. For example, ice is a very low amount of friction. Therefore, it could slide very easily over it. Versus a carpet, which has a much greater degree of friction. Another important force that we'll be talking about is gravity. Okay, and so gravity is, we learned about gravity a little bit when we talked about mass. Okay, gravity is an attractive force between two objects. And we learned previously that the force of gravity depends on the size of the objects, the mass of the objects, and also the distance between those objects. We kind of talked about it in relationship to planets, in that, a larger planet will have a stronger force of gravity attracting objects to it, and a smaller planet will have a lower force of gravity. Okay, so we'll be including these forces of friction, gravity, as we move on through this section of our notes. Oh, by the way, I'm using a new software to record this. That's why you see me there. So Newton's first law of motion is sometimes called the law of inertia. And sort of the law says, it's in quotes here, an object at rest tends to stay at rest. An object in motion tends to stay in motion with the same speed and in the same direction unless acted upon by an outside force. This is called inertia. Basically what it's saying here is that objects that are moving or that are still will continue to do whatever it is they're doing unless some force changes that. For example, if you have my coffee mug here. Okay. So right now my coffee mug is still. It's at rest if we're thinking about Newton's first law. And it's going to stay at rest. Okay. The forces that are currently acting on my coffee mug are balanced. Now, if I push the mug, okay, I could then cause it to move. Okay. And so the force that I apply to that coffee mug causes it to move. That's that outside force. Well, then you might ask a question. Try and do this again. If I have this little mini Cadbury egg, pretty good. Okay, right now it's at rest. It's going to stay at rest. If I touch it, it will move. But you might say, well then, what about Newton's first law? If I move this, Newton's first law says that if it's in motion, it should stay in motion. Okay, unless acted upon by an outside force. But you'll notice the egg does stop moving. It doesn't continue moving. So why is that? And the answer is friction. As this egg moves across the surface of my table, there's friction between the egg and the table, and so that force is what actually slows down this egg, causing it to stop moving. Imagine if I had a friction-free surface here. If somehow I can remove all friction between this Cadbury egg and the table, if I slid this forward, it would just continue moving across the table because there would be no force of friction slowing it down. Okay. But here on Earth, okay, in most of our everyday interactions, there is friction. So objects, if you roll a ball across the floor, it will stop, again, because of friction. So that's Newton's first law. Okay, let's look at this again. Let me just finish eating my chocolate egg. Feel free to fast forward a couple seconds. Okay, I'm back. So, Newton's law says an object at rest will stay at rest. So, if you think about, maybe you've seen people do this tablecloth trick here, where they have a table set with plates and dishes and things, and then they whip out the tablecloth very quickly. Let's see, can I do an example? Let's try. All right. Let's go back down here. All right. So, I have my coffee mug. I have my tablecloth. So if I yank out this tablecloth, okay, what happened? Well, the coffee mug was at rest because of Newton's first law of inertia. Its tendency is to stay at rest. I yanked out that paper, causing it to slide out from underneath, and the coffee mug stayed where it was. That's inertia. Okay, an object in motion will stay in motion. Not will stay in motion. So, an example here, if we have a crash test dummy inside of a car that's moving forward, if it's not wearing the seatbelt, and then the car suddenly stops by having this collision, so the car is stopped. However, the crash test dummy inside, because of Newton's first law, is going to continue moving. It was moving forward with the speed of the car. The car stopped. However, crash test dummy continued moving and gets propelled out of the car. Okay, so objects at rest will stay at rest. Objects in motion will stay in motion. Unless, here's the important part, unless acted upon by an outside force. I thought these used to be animated. I guess they're not working. But again, if this motorcyclist hits this brick wall, motorcyclist continues along, okay, because of the law of inertia. Now, this is also the reason why wearing your seatbelt in the car is so important. Because as you're traveling forward, if there's a sudden stop, okay, your tendency of your body is to continue moving forward. The seatbelt, however, sort of anchors you to the car, and so as the car slows down, you press forward against your seatbelt, and you will slow down as well instead of continuing in motion out of the car. This is also why when you're driving with your parents and they're driving a little bit too aggressively and they hit the accelerator and the car speeds up very fast, think about how that feels if you're the passenger. Okay, you are at a stoplight at rest. When your parent hits the accelerator, that car starts moving forward, but your body was at rest, and so the back of the seat pushes into your back. And that's why we feel like we're being pushed back, but actually the car is moving forward while we're still, and the back of the seat is pushing against us. Okay, let's talk about Newton's second law of motion. Newton's second law of motion has a... Hey, Finn, I'm going to have a guest appearance here. Hold on one second. Come here. Is this Finn? So, Newton's second law of motion says that this has a formula with it, an equation. It's pretty simple. But Newton's second law of motion says, okay, that an object will move in the same direction, okay, that the force is applied, okay, and the acceleration of that object will depend upon its mass and the force that's applied. So sort of just as common sense a little bit. If we think about this shopping cart in your notes, okay, one is empty, one is filled with, let's say, gravel or something. Okay, so which cart are you going to have to exert a greater force on to cause it to accelerate? Obviously, you'd have to exert a greater force pushing that cart full of gravel, because if we look at the formula, the mass is greater. Therefore, you're going to have to exert a greater force. Okay? Or if we had two objects of the same mass and we apply a greater force on one of them, that object is going to accelerate more quickly. It's going to move faster. Okay, so Newton's law tells us that with the more force that's applied, all right, he doesn't want to be here anymore. There you go, good boy. He's running away, scared. So the more force applied to a given mass will accelerate it faster. So let's look at some examples of this and how we might use this equation. Okay. Mike here, in this problem, his car is out of gas. The car has a mass of 1,000 kilograms. Okay. So Mike's going to try to push his car to the gas station. And so he pushes his car. He's able to accelerate it 0.05 meters per second squared. So let's use Newton's second law and figure out how much force is Mike applying to this car to do that. So we start with our equation. So force equals the mass times the acceleration. We know that the mass of the car is 1,000 kilograms. It's been accelerated 0.05 meters per second squared. So we do our math, and we get an answer of 50 kilograms times meters per second squared. Sort of a strange unit. But there's actually a unit that scientists have that equals 1 kilogram times meter per second squared. And the name for that unit is the Newton. So 50 kilograms times meters per second squared is equivalent to 50 newtons of force. Okay, let's look at Bob. Bob has a van. Okay, also out of gas. And Bob's pushing his car to the gas station. He also accelerates it at 0.05 meters per second squared. Using Newton's second law, how much force is Bob applying? You probably don't even really need to do the math. Okay, if you just think about this. Okay, Bob's van is double the mass of Mike's car. Therefore, what force is he going to have to use? If you just think it's double that, you're correct. We could go through the formula, 2,000 kilograms times 0.05 meters per second squared, giving us an answer of 100 newtons. Bob has to apply twice as much force to accelerate his van because it has twice the mass. This brings us to Newton's third law. Newton's third law states every action has an equal and opposite reaction. Or you might say every force has an equal and opposite force. So what this law says is basically that forces come in pairs. Okay, hopefully you never punch anybody in the face. But if you were to do that, not only is your hand applying a force to the person's face, but the person's face is applying an equal force on your hand. Okay. Think about a rocket. Okay. Rocket engines, jet engines work by employing Newton's third law. Okay. As high velocity particles are emitted, released from one end of the engine, those molecules coming out with great velocity have an opposite action. So that force of those molecules being released has an opposite force on the rocket, and that force is what causes it to move forward. Look at some other examples. If you've ever done this, if you tried to jump from a boat onto a dock or something, okay, we know that as you push off from this boat, propelling yourself forward, your foot also exerts the opposite force on the boat, causing it to move backwards. So it's another example of Newton's third law. If you imagine two people on ice skates on a skating rink, and if they push on each other, they're exerting force on each other, but there's an opposite force also interacting there that pushes them apart. If you go to a skating rink, you push on the board on the wall. So you push, you're exerting a force. It exerts an opposite force on you, and you move backwards. The greater force you apply, the faster you move backwards. Okay. So let's say Bob, maybe a better name for him might be Tom. Let's call him Tom. He's tired of pushing the van. He's getting too tired. So he has an idea. He says, I'm much better, faster on rollerblades than when I'm walking. I'm going to put on my rollerblades. And then I'm going to push this van. That's going to help. So Bob goes up to the van on his rollerblades. He's going to exert a force of 100 newtons on that van. However, now because he's wearing these rollerblades, there's going to be less friction between his foot and the ground. As he pushes on that van with 100 newtons of force, it's pushing back on Bob with 100 newtons of force, and that's going to send him moving backwards. Firing a gun, for example, another example of Newton's third law of motion. Okay, when a person fires a gun, the bullet comes out of that with great force, with great acceleration. But that's the force. There's also an opposite force that pushes back on that gun. Okay, and that's why there's kickback or recoil. Some of you guys that play video games, depending on which weapon you're using, if you're playing Call of Duty, depending on which weapon will have different amounts of recoil that after you fire it, there's that kickback. Okay, smaller guns that fire bullets with less velocity, or smaller bullets will have less of that force, that recoil. So if we just sort of summarize Newton's laws. Okay. First law is the law of inertia. The objects will stay at rest or stay in motion unless they're acted upon by some outside force. Just looking at a book sitting on a table is an example of Newton's first law. Newton's second law says that the more mass an object has, the harder it is to move. The more force will have to be applied to it to cause it to move. It does have a mathematical expression. F equals ma. Force equals mass times acceleration. So if you helping your parents work around the house in the backyard over this break, they ask you to take a big wheelbarrow full of branches that they had cut down to the road. It's going to take more force to push that loaded wheelbarrow to the curb. Once you empty it out and push it back, it's much easier. You have to apply much lower force because the mass is less. Newton's third law: every action has an equal and opposite reaction. Okay, you push against the wall pushes back on you. So those are Newton's three laws. I'm going to finish up with just a couple other things. So let's talk about gravity for a second. So gravity is the attractive force between two objects or two masses. We are most familiar with gravity here on Earth because that's where we live. And so gravity, the force of gravity will change slightly if you're up on very high elevation of a mountain or deep in a valley, but not to a very significant level. So overall, what we're going to say is that the force of gravity, the acceleration due to gravity, is relatively constant. It's 9.81 meters per second squared. If you take an object and you drop it, well, gravity is exerting a force causing my pen to accelerate at a rate of 9.81 meters per second squared. Okay? And that's a constant acceleration. All objects fall to the earth at that same rate. So if you were to drop a tennis ball and a baseball at the exact same time, and the baseball obviously has a higher mass than the tennis ball. Okay, if you drop them at the exact same time, what would you expect if acceleration is constant? You would expect them to hit the ground at the same time. You could try this if you have a baseball and a tennis ball or a lacrosse ball or whatever. Even if they have different masses, if you drop them at the exact same time, they should hit the ground at the exact same time because they're both accelerating at 9.81 meters per second squared. Okay. Sometimes people assume that the more massive object will hit the ground first, but that's actually not the case. But let's take another example. What if you have a baseball and a feather? I just said that all objects drop to the earth because of gravity at the same rate. But what would happen if I dropped a feather in a baseball? Obviously, the baseball is going to hit the ground first, and the feather is going to take much longer to hit the ground. So why? Are those two things I'm saying contradictory? Well, not really, because there's another factor here. Even though the acceleration due to gravity for the baseball and the feather is 9.81 meters per second squared, as they fall to the earth, there's another force at play. That's air resistance. Because as those objects are falling, air resistance is slowing each of them down. However, because of the shape of the feather compared to the shape of the ball, air resistance on the feather is much greater, and therefore it gets slowed down more as it's falling. So that might lead you to ask the question, well, what happens if you were able to drop the feather in the baseball in a place where there was no air resistance? What would happen? What do you think? Well, to see somebody actually do this, there's a video that's going to be linked tomorrow. You could actually see what would happen. All right, our final topic we're going to just mention here is this concept of momentum. So momentum is, you could sort of think of it as how difficult it would be to stop a moving object. Okay. To calculate the momentum of an object, we multiply its mass times the velocity that it's traveling. So, for example, if we had a gorilla rolling barrels down at a small Italian plumber, and he's rolling these barrels, which each weigh 50 kilograms, and he's rolling them at a speed of a velocity of 10 meters per second. What is the momentum of those barrels? Well, we've read our formula. Momentum equals mass times velocity. Substitute our numbers. Come up with our answer. The momentum of each barrel is 500 kilograms times meters per second. If you rolled the barrels faster, the momentum would increase. If the barrels were more massive, the momentum would increase. Okay, so let's think about an example, a football example. If you're playing football and you're going to get tackled by somebody. Let's say a 200 kilogram linebacker, it's a big linebacker, was running at you at a velocity of 2 meters per second, was going to tackle you. Or there's going to be a much smaller player, a 100 kilogram safety, running at you to tackle you, but they're running at 4 meters per second. Which one would hurt more? Which one would have greater momentum? Well, they'd have the same. Okay, because the safety has half the mass, but the safety is running at double the speed. And so they're going to balance out. They would each have the same momentum. So let's imagine if you have a bowling ball and a marble. It's my table then. So if you have a bowling ball This is not going to work that well. A large bowling ball rolling against a small marble. If they're rolling at the same speed and collide, what would happen? Well, because the large ball has greater momentum when they meet, okay, it would be push this marble in this direction. Okay? What if I had two equal-sized balls? Same mass, moving the same speed, they would collide, and then they would bounce, and they would be moving apart at the same speed because they had the same momentum. Could you ever have a large bowling ball and a small marble that have the same momentum? Well, you could. If the marble was rolling very fast, the bowling ball was going very slowly, then they could have the same momentum. Okay. So momentum is dictated by both the mass of the object and its velocity. Okay, so that's going to be the rest of our notes on Newton's laws in motion. Covered a lot of different concepts here. The next couple days you're going to be doing some online simulations, reading about some situations and trying to understand how Newton's laws apply, looking at how Newton's laws apply to a toy. So we're going to do a lot of activities here in the next couple days that help you understand these laws and how they apply. Okay, there's tons of videos you can find about these laws. I'm going to post some of them, and tomorrow what I'm going to have you do is look at some of these videos. Because a lot of these things are sort of visual, and so because I'm just doing this here in my dining room, sitting at a table, I can't show you a lot of these things, but I'll find some videos that will help these concepts to sort of for you to see how they apply. So that's it for today. I hope you have a great day. It's a little bit rainy outside, so maybe you could use this time to come up with a new branch of mathematics like Newton did. So have a great day.